Okay, so this video refers to lecture 4 moments, and specifically is looking at couples and using couples in moment calculations. So a couple is very simply a pair of forces with equal magnitude, opposite direction, and they're separated by perpendicular distance d. Alright, so that is a couple. Just make my pen a bit smaller. So, why would you use couples? Well, a very simple example would be something like on slide number 39 in lecture 4. You've got the steering wheel of a vehicle. If you have a larger steering wheel, then you have a larger perpendicular distance between your hands. So if we imagine that's a steering wheel and you're trying to turn a corner, the bigger steering wheel here, you can put the same force into the turn, but you have a bigger turning effect, bigger moment, because the perpendicular distance between your forces is bigger. So the effect is bigger, so you have to put in less force to achieve a large moment. And there's two ways of finding moments. Using scalar techniques, scalar analysis, a moment about a point is simply a force times a distance. So the magnitude of one of your forces times the perpendicular distance between them, and that point O will be somewhere in the middle of those two forces. So for instance, F HD, point O will be somewhere in the middle there. And so your moment will be the magnitude of one of the forces times the distance between both forces. And similarly we can do vector solutions for this, where it would be R crossed with F, your position vector crossed with your force vector, but your position vector in couples is the vector that defines the spacing between the two forces. And then what you can do is you can start to resolve multiple moments into one moment. If we turn to, I'm going to look at slide 42, which gives a scalar example of this. So I'll just draw the diagram and then we'll go through it. So this is question 1 from slide 40. And you've been asked to find the force F, so that the resultant moment is 1.5 kilonewton meters clockwise. So if we're calling anti-clockwise positive as its standard, the sum of our moments is equal to minus F, so I'm just going to choose this force here, and I'm going to look at times in that by the distance between my two forces, which is 0.9 meters, and apologies, I've just done what I've told you not to do. So this minus relates not to the direction of the force, it relates to the direction of the moment, but you already have spotted that. So the direction of the moment, the direction of the couple, is both of those forces are trying to turn it clockwise, the F forces, so it's a minus. I've also got 2 kilonewtons, 0.3 meters apart, and both of those are trying to turn it the other way. They're trying to turn it anti-clockwise, so they are positive. And I want that to add up to 1.5. So now all I do is rearrange that equation to find F, and F comes out at 2.33 kilonewtons. So we can also do the vector approach. So if you look at slide 44 on the lecture, it's asking for a couple moment in Cartesian vector notation. So we know that a moment is a position crossed with a force vector. We also know from our diagram that our position vector, how we get from the distance between those moments, if you like, between those forces, sorry, if you like, is 0.4 in the I direction. My force as a vector is going to be 0 newtons in the I direction, and then we'll resolve it into J and K as we have done before. So it's plus 4/5 of 450 J minus 3/5 450 K, and that's just looking at the force FB, which is marked in the diagram. We could have chosen FA instead, doesn't really matter. So that would be 0 I plus 360 J minus 270 K. And the final part of that we do our matrix. So I, J, K, 0.4, 0, 0, 0, 360 minus 270. So we're going to do 0 times minus 270 minus 0 times 360 I. We're going to do minus because it's the J section. 0.4 times minus 270 minus 0 times 0 plus what we've got left, 0.4 times 360 minus 0 times 0. And if I put that into my calculator, I get 0I plus 108J plus 144K. So that's my moment as a Cartesian vector. So there are now some examples for you to have a go at. If you have a go at group problem solving exercise 1 and 2, beginning on slide 47, and then come back to this video and I'll show you how to solve them. So this part of the video refers to the solution to the first group problem solving exercise on couples, beginning on slide 47, which you should have had a go at on your own already. You may find it more beneficial to look at the actual slide rather than my terrible drawing. But hopefully all the information is there. So the first thing you're going to do is resolve your forces. So we'll start with the 30 kilonewton forces on the top beam and resolve them into the Y direction and the X direction. Now when you look at those forces, the Y components clearly make a moment, so Fy minus Fy, they clearly have a moment, a couple, a turning effect. The X components have 0 meters between them, i.e. they're on the same line. There is no perpendicular distance between them, so only the Y component, which has a distance shown in red, only that contributes to the turning effect of the moments. That's the only one we need to worry about for our resultant couple. So we're going to have Fy for this top beam is going to equal 4/5 of 30, and that's 24. So the x components, because there's no perpendicular distance between them, they're acting in the same line, they do not contribute to the couple. Similarly, we can resolve our 15 kilonewtons into x and into y, into x, and you can see that similar situation exists in that the y components exist in the same line, whereas the x components have a perpendicular distance between them. So the fx for this pair of forces is 15 cosine 30. 15 cosine 30 is not given to me, so you can work that out with your own time. But if you did put it in a calculator, you'd get something like 12.99 kilonewtons. So now we can do our moments. So our moments, some of our moments is going to be 24 times 2, represented by the red line here. 24 times 2, they're going to try and turn our beam. They're going to be turning clockwise, so we put a minus sign on there. And our other pair of forces are also going to try and turn clockwise, so we put a minus sign there, and it's going to be 12.99 times 2, because it's 2 meters between those as well. So the sum of our moments is going to be minus 73.98 kilonewton meters, or you could say 73.98 kilonewton meters clockwise. So that's how you solve the first group problem solving exercise on couples. There's a second group problem solving exercise on couples beginning on slide 50. If again you pause the video, have a go at that, and then come back to it and I'll show you how to solve it. So this is looking at the group problem solving exercise number 2 on couples, which begins on slide 50 of lecture 4. And you've been asked to find the couple moment acting on the pipe assembly. So this should look like a rough sketch of the question shown in the diagram on the slide. And you know that a moment is a position vector times a force vector. Particularly for couples, the r vector will refer to the distance or the position of the two forces relative to each other. And our two forces are acting, one here and one here, and that's A and B. So to get from A to B, RAB, we have to move in the x direction from 200 to 300 millimeters, so 0.1 meters. Don't need the m, but we do need an I, sorry. In the j direction, we have to move 300 plus another 200, so 500, or 0.5 j, and they're in the same plane, so there's no z component, so 0k, but I'll just leave it off. And my force, we've been told in the question, is 15k. So now all I need to do is put those into a matrix. So my moment is equal to 0.1, 0.5, 0, my position vector, 0, 0, 15, my force vector. So we're going to start with 0.5 times 15 minus 0 times 0, I, minus, because it's the middle bit, 0.1 times 15 minus 0 times 0 j plus what we're left with 0.1 times 0 minus 0.5 times 0. Okay, if I then put that into my calculator, the final result should be my moment equaling 7.5 minus 1.5 J Newton meters. So that concludes the group problem solving exercises on couples, and indeed the video on how to solve couples and looking at couple moments. The following videos will then go on to talk about simplifying larger systems using this technique and others that we've looked at in previous videos.